A passing train creates a perfect illusion of motion. For a split second, you genuinely cannot tell if you are the one moving or if it is the other train. This common experience is a direct gateway into the true nature of spacetime. Albert Einstein wove space and time into a single, dynamic fabric, and learning to think within this framework is the key to unlocking the universe's greatest secrets. By the end of this journey, you will possess the mental toolkit to visualize reality through the lens of relativity, transforming how you see everything from a falling apple to the edge of a black hole. We will uncover why two perfectly honest observers can disagree about what happens at the same moment, and how the entire cosmos enforces a strict speed limit to protect the flow of time itself. What does it truly mean for the future to be already written in the stars? That fleeting ambiguity on the station platform cuts straight to the heart of physics. Each passenger on those passing trains is perfectly justified in believing they are the one sitting still. From your window, the other train slides past, its passengers blurred by motion. But from their window, you are the one rushing by. Who is correct? The astonishing answer is that both of you are. This is the principle of relativity, a concept refined by Galileo and later made absolute by Einstein. Each train represents what physicists call an inertial frame of reference. Think of it as your personal, moving bubble of reality, a coordinate system where, if no forces are pushing or pulling you, you will continue to move in a straight line at a constant speed. The truly profound part is this: the laws of physics operate identically inside every single one of these inertial frames. Whether you are standing on a platform, cruising on a train, or orbiting the sun, a dropped ball will fall straight down to your feet according to the same rules. There is no experiment you can conduct inside your sealed, moving train car that will reveal whether you are in motion or at rest. This means no frame is special. None can claim the ultimate title of being absolutely stationary. This principle shatters our everyday intuition. We feel as though we can point to something and say that thing is truly moving. But from the perspective of a speck of dust on that moving car, the entire universe is whirling around it. This foundational idea forces a dramatic revision of our concepts of space and time. If the laws of physics are the same for everyone, regardless of their state of uniform motion, then our most basic assumptions about simultaneous events cannot be trusted. Two flashes of light that appear to happen at the same instant for an observer on the platform may occur at different moments for a passenger on the train. Einstein himself articulated this radical shift in his 1905 paper on the electrodynamics of moving bodies, writing, "The same laws of electrodynamics and optics will be valid for all frames of reference." This single sentence dismantled the idea of a universal now, setting the stage for a new reality where space and time are inextricably woven together into a single fabric. This single fabric of reality demands a new kind of address. Every event, from the blink of an eye to the explosion of a star, requires 4 coordinates to pinpoint its location, not just 3. You need to know where, but you also absolutely need to know when. This is the profound shift in thinking introduced by Hermann Minkowski, Einstein's former teacher, who transformed the theory of relativity into the geometric picture of spacetime. He famously declared that henceforth space by itself and time by itself were doomed to fade away into mere shadows. Only a kind of union of the two would preserve an independent reality. He gave us the map for a 4-dimensional continuum, a stage where every object traces out a unique path called a world line. Think of a loaf of bread. Each slice represents the entire universe, all of space, frozen at a single instant. Now stack those slices in order. Your world line is the unique path you carve through that entire loaf, from the crust of your birth to the end of your journey. Alternatively, imagine a roll of film. Each individual frame is a snapshot of space at one moment. Your life is the entire film strip, a long, twisting thread weaving through those sequential frames. This four-dimensional picture holds the key to a deep mystery, something that remains constant for all observers, no matter how fast they are moving. While two people might disagree on how much space is between two events, and they might fiercely argue about how much time elapsed between them, they will always agree on the space-time interval. This interval is a combination of the spatial and temporal separations, a single measurement that fuses distance and duration into one immutable truth. It is the true distance between two events in the four-dimensional fabric. This is what resolves puzzles like the famous twin paradox. One twin stays on Earth, while the other travels to a distant star at near light speed and returns. The traveling twin comes back younger. In the old way of thinking, this seems contradictory. If all motion is relative, why isn't each twin justified in saying the other was moving and should therefore be younger? The answer lies in their world lines through the space-time loaf. The stay-at-home twin's path is relatively straight. The traveling twin's path, however, has a kink, a turn at the star where they must accelerate to come back. Their journeys through the four-dimensional continuum are not identical. One path is genuinely longer through space-time than the other, and this difference is objectively real, explaining the difference in their aged clocks. Seeing reality as this single, unified entity is the essential foundation for understanding the universe's ultimate traffic laws, the light cones that govern cause and effect. This cosmic speed limit is absolute and unbreakable. Picture yourself on a starship hurtling through the void at 99% of the speed of light. You turn on a flashlight, pointing it forward. Common sense screams that the light beam should crawl away from you at a mere 1% of light speed. But that is not what happens. The beam of light races ahead at the full, unwavering speed of light, exactly as if you were standing still. This is not a theoretical guess. It is a cornerstone of the universe, a postulate of special relativity first proposed by Einstein, which states that the speed of light in a vacuum is constant for all observers, no matter how fast they are moving. This stunning fact was confirmed by the famous Michelson-Morley experiment in the late 19th century, which sought to measure our motion through a hypothetical light-carrying medium called the ether. They found nothing, no matter which way they turned their apparatus or how the Earth moved in its orbit. The speed of light they measured never changed. This constancy has profound and bizarre consequences for space and time themselves. To keep the speed of light the same for everyone, time must stretch and space must contract. This is where time dilation and length contraction come into play. A perfect example rains down on us from the sky every second. Cosmic rays from deep space strike our upper atmosphere, creating short-lived particles called muons. These muons are so unstable that they should decay into other particles after traveling only about 600 meters. Yet they are created over 10 kilometers up, and we detect them constantly at the Earth's surface. How do they make it so far? From our perspective on the ground, their incredible speed means their internal clocks are running slow. Time for the muon is dilated. A journey that takes several microseconds from our point of view might feel like only a microsecond from the muon's own frame, allowing it to reach the ground before it decays. From the muon's perspective, it is at rest, and it is the distance to the ground that has contracted, shrinking to a length it can traverse in its brief lifetime. This mutual adjustment of space and time also reshapes our understanding of motion itself. As any object speeds up, approaching the cosmic speed limit, its energy and momentum do not simply add up in the old, intuitive way. They transform. To accelerate the object further requires ever-increasing amounts of energy. Pushing it all the way to the speed of light would require an infinite amount of energy, an obvious impossibility. This relationship between energy, momentum, and mass is crowned by the most famous equation in all of science, E equals mc squared. This simple formula reveals a universe where mass is not just stuff, but a colossal, concentrated form of energy. The annihilation of a tiny speck of matter can release a staggering amount of power, a principle that explains the energy of the sun and the destructive force of nuclear reactions. As physicist Brian Greene once noted, the speed of light is not just a limit on velocity, it is a limit on causality itself. This universal speed limit is the ultimate traffic law of the cosmos, and it is absolutely essential for constructing the next piece of our mental toolkit, the light cones that will finally show us what events in the past can truly affect our present and what our present can possibly influence in the future. Our daily navigation relies on a system that would fail without the principles of spacetime. The Global Positioning System, a network of satellites orbiting high above Earth, must correct for relativity to give you accurate directions to the nearest coffee shop. From our perspective on the ground, two strange things are happening to the atomic clocks on those satellites. First, because they are moving at thousands of meters per second relative to us, special relativity dictates their clocks tick slower than ours, a result of time dilation. Second, because they orbit in a region where Earth's gravity is weaker, general relativity dictates their clocks tick faster than ours, a result of gravitational time dilation. These two effects do not cancel out. The gravitational effect is stronger, so overall, the satellite clocks gain about 38 microseconds each day compared to clocks on the ground. This seems tiny, but because light travels nearly 300,000 kilometers in a single second, an uncorrected clock error would cause your position to drift by several kilometers each day, rendering the system useless. Engineers must deliberately program the satellite clocks to run slow before launch, so they will tick at the correct rate once in orbit. This is not abstract physics. It is a daily, practical application of thinking in frames of reference. The GPS satellites are in a state of free fall, tracing inertial paths through curved spacetime. Their frame is nearly inertial, like our smoothly moving train. Compare this to the frame of a car accelerating away from a stoplight. In that car, you feel pushed back into your seat. From your perspective inside this non-inertial frame, it feels exactly as if a mysterious force field has suddenly appeared, pulling you backward. This is the genius of Einstein's equivalence principle. He realized there is no local experiment you can perform to distinguish between the force you feel in an accelerating rocket ship in deep space and the force you feel standing still in a gravitational field. Acceleration and gravity are equivalent. This profound insight was the bridge from special to general relativity, forcing Einstein to describe gravity not as a force, but as the curvature of spacetime itself. A massive object like Earth creates a dip in the fabric, and the GPS satellites are simply following the straightest possible paths called geodesics through that curved geometry. This frame-dependent reality resolves puzzles that seem like pure magic. Take the famous ladder paradox. A farmer has a 10-meter-long barn with doors at both ends. Her friend runs toward the barn carrying a 10-meter-long ladder. From the farmer's frame, the high-speed ladder is length contracted. It appears shorter than 10 meters, so she can, for an instant, slam both doors shut and capture the entire ladder inside her short barn. But from the runner's frame, it is the barn that is moving toward him, and thus the barn that is length contracted. From his perspective, the barn is shorter than 10 meters, so there is no way the entire ladder can fit inside at once. Both observations are correct within their own frames. The resolution lies in the relativity of simultaneity. The events of the front door closing and the back door closing, which are simultaneous for the farmer, are not simultaneous for the runner. He sees the doors close at different times, allowing the ladder to fit without being crushed. This is not an illusion. It is a fundamental property of spacetime, where measurements of length and time are woven together. These frame effects become extreme near the most massive objects in the universe, near a rotating black hole. As physicist Kip Thorne's work on frame dragging showed, the black hole does not just sit in spacetime. It spins, and in doing so, it twists the very fabric of spacetime around it, like a spinning spoon twisting in a jar of honey. Any object falling toward it is forced to rotate with the distorted frame, an inescapable vortex where the concept of standing still becomes impossible. Mastering these frames of reference, from a simple train to a warped black hole, gives us the ultimate decoder ring for the cosmos. It allows us to translate observations from any vantage point, to understand that reality is a tapestry of interwoven perspectives, all equally valid within their own context. This mastery is the final preparation we need to map the ultimate boundaries of reality, the light cones that will finally show us the true architecture of cause and effect. That map of frames and world lines finally gives us the tool to draw the ultimate boundaries of reality. Take a single, solitary event, a flash of light at one specific place and one specific moment. From that spark, light radiates outward in all directions, not just through space, but through spacetime itself. If you could plot this on our four-dimensional map, with one direction of space flattened out for simplicity, the light would not form a sphere. It would trace out a double cone, a structure known as the light cone. This cone is not a physical object. It is the absolute architecture of cause and effect. It carves the entire universe into three distinct and unchangeable regions relative to that flash. The inside of the cone, stretching downward from the event, is its past light cone. This contains every single event in the entire cosmos that could possibly have sent a signal, any signal, even one moving at light speed, to arrive at that flash. It is the entire history of its possible causes. The inside of the cone reaching upward is its future light cone. This contains every event that the flash can possibly influence. Any action, any message, any consequence of that flash must lie within this region. Then there is the vast outside, the region physicists call elsewhere. Events in the elsewhere are causally disconnected from our flash. They are so far away in space or so close in time that not even a beam of light could bridge the gap between them and our event. Nothing that happens in the elsewhere can be a cause of our flash, and our flash can have absolutely no effect on anything in the elsewhere. The slope of the cone's sides is fixed by the universe's ultimate speed limit. Because light always travels at the same constant speed for everyone, the cone always opens at the same angle on our spacetime diagram. This is why all observers, no matter how fast they are moving, will always agree on the fundamental structure of a light cone. They might disagree on the precise coordinates of an event inside it, but they will all agree that the event is inside. They will all agree on the causal relationship. As Stephen Hawking profoundly stated, the light cone defines the boundary of the possible. This structure is the universe's rigid law of connection, but this geometry is not always perfectly straight. In the curved spacetime near a massive object like a star or a black hole, the light cone itself begins to warp. The immense gravity bends the paths of light, causing the entire cone to tilt toward the source of the gravity. It is as if the fabric of reality is a sloping hillside, and the light cones are like trees growing at an angle, all leaning in the same direction. Near the event horizon of a black hole, this tilt becomes so extreme that the entire future light cone points inward. Within that region, every possible future, every path that light or matter can take, leads toward the black hole's center. There is no future left in the elsewhere. The light cone becomes a one-way street into the abyss. This graphical tool is indispensable. It allows us to see at a glance why you cannot outrun your past, why some stars are forever beyond our reach, and how the universe meticulously enforces a chronological order that protects the flow of cause from paradox. The light cone is the final piece that reveals how our local frames of reference are all stitched together into a single, coherent, and causal cosmos. An event inside your future light cone is not just a point on a map. It is a destination you can actually reach, a moment you can truly influence. Suppose you receive a message from a civilization orbiting a star 100 light-years away. That signal, that entire conversation, exists squarely within the domain of your possible future from the moment it was sent. You are connected by a thread of causality that light itself has woven. This is the realm of possible influence, a volume of spacetime where your actions have meaning and your past has consequences. Any object with mass, like a starship or a human being, must always travel on paths inside this future light cone. Physicists call these time-like paths because the movement through time is always greater than the movement through space. You are always progressing into your future, never quite catching up to a beam of light. Light itself, and anything else moving at the ultimate speed limit, travels on the very surface of the cone along what are called null paths. For light, the journey through space exactly balances the passage of time. From a photon's perspective, if it had one, its entire trip across the universe takes zero time. It is emitted and absorbed in the same instant. This structure enforces a profound personal clock, known as proper time. This is the time measured by a clock that follows a specific world line through spacetime. It is your own lived experience, the time that passes for you. Crucially, different paths between two events will accumulate different amounts of proper time. This is the true resolution of the twin paradox. The twin who travels to the star and back follows a longer, curved path through the four-dimensional continuum. Their world line, when you calculate its total length, is actually shorter in terms of space-time interval. They experience less proper time, they age less. Their journey through the loaf of bread simply covers less bread. This is not an illusion of slow clocks. It is a fundamental difference in the geometry of their lives. This entire architecture exists to protect one sacred rule. Causality must be preserved. A cause must always come before its effect for every single observer, no matter how they are moving. The light cone makes this certain. Because the inside of the cone is an absolute region, every valid frame of reference will agree that a cause inside the past light cone happens before its effect inside the future light cone. This rigid structure prevents paradoxes from unraveling reality. You could never, for example, build a machine that sends a message into your own past to prevent your own birth. Any such message would have to travel outside your light cone, into the forbidden realm of elsewhere, which is utterly impossible. The universe will not allow you to become your own grandfather. We see this causal history written across the sky. The cosmic microwave background radiation, the faint afterglow of the Big Bang, lies firmly within our past light cone. This ancient light has finally reached us after a journey of over 13 billion years, delivering a baby picture of the cosmos. It is a message from an event that could and did influence everything we see today. Grasping the interior of the light cone is to understand the ultimate limits of your agency. Your future is not a blank slate. It is a cone of possibility, a domain of events you can still shape, bounded by the unchangeable laws of a four-dimensional universe. The region outside the light cone is a profound and permanent isolation. Two events placed here in the elsewhere are separated by a space-like interval, a gulf so wide in space and so narrow in time that not even light could bridge it. These events are causally disconnected, forever strangers in the cosmos. They cannot influence each other no matter what. This leads to one of relativity's most mind-bending consequences, the absence of a universal sequence. For two such events, their time order is not a fact of the universe, but a matter of perspective. One observer moving in a certain way might confidently record that event A happened before event B. Another observer moving at a different velocity could just as truthfully report that event B occurred first. Both are correct within their own frames of reference, and neither sequence is more real than the other. The universe simply does not decree which space-like separated event comes first. This is possible because the fundamental spacetime interval between them is space-like, meaning the spatial distance is greater than the distance light could travel in the time between them. This ensures that no signal, no particle, no information of any kind can ever travel from one to the other. Consider a supernova explosion in a galaxy a million light-years away. The light from that cataclysm reaches us today, a message from an event that is firmly in our past light cone. But from the perspective of that exploding star, our present moment on Earth is in its elsewhere. Any signal we send out right now, at the very instant we see the explosion, would take a million years to reach that galaxy. The supernova event is long over, its debris cold and scattered. Our message arrives to an empty stage, unable to affect the outcome of a drama that concluded eons ago. This absolute separation might seem challenged by the strange phenomenon of quantum entanglement, where two particles can share a connection such that measuring one seems to instantly influence the other, even across vast distances. Yet, and this is the crucial point upheld by relativity, this quantum connection cannot be used to send a faster-than-light message. The outcome of a measurement on one particle is random and cannot be controlled by an observer. Without the ability to encode a deliberate signal, to transmit a specific piece of information like a word or a number, causality remains perfectly safe. The two particles may be correlated in a way that seems spooky, but they cannot be used for communication. This preserves the sanctity of the light cone. As physicist Sean Carroll reminds us, the elsewhere is a region of no causal contact, a reminder of the universe's vastness and isolation. Understanding this region is not just an academic exercise. It emphasizes the profoundly structured nature of reality, where the light cones act as cosmic traffic controllers, ensuring that cause always precedes effect, and that the flow of time, however relative it may seem, never leads to a logical paradox. This architecture of impossibility is what makes the possible so meaningful, framing the entire causal tapestry of our lives within the absolute boundaries of the light cone. Every single object in the universe carves its own unique thread through the four-dimensional fabric of reality. This is its world line, a continuous curve that tells the complete story of its existence, marking every location at every single moment from its beginning to its end. Think of it as the permanent groove your life leaves in the grand loaf of spacetime, a record that is always being written but never erased. For any object with mass, this world line has a crucial restriction. At every point along its journey, its path must always remain inside its own future light cone. It can never point outward into the forbidden elsewhere. This is the geometric expression of the cosmic speed limit, a mandate that says you can approach the boundary, but you can never cross it. light itself, and only light, travels along the surface of this cone, tracing paths known as null geodesics. For a photon, the entire trip from a distant star to your eye is a single point in its own experience, a journey with no passage of time at all. This elegant picture becomes even richer when we introduce gravity through general relativity. Here, world lines are not about forces in the old sense. A planet orbiting a star is not being pulled by an invisible string. Instead, the star's mass warps the spacetime around it, creating a deep curvature. The planet is simply following the straightest possible path through that warped geometry, a path called a geodesic. It is like a marble rolling around the inner surface of a bowl, its curved orbit being the most direct route available in that distorted landscape. We can categorize these world lines by their shape. In the flat, gravity-free void of empty space, an object with no forces acting on it will trace an inertial world line, which is perfectly straight in spacetime. The moment you fire a rocket engine, however, your world line curves. This accelerated path represents a departure from free fall, a conscious bending of your trajectory through the continuum. The passage of time you personally experience is measured along this world line as your proper time. It is the reading on a wristwatch you wear, the accumulation of moments that is uniquely yours. Crucially, the total amount of proper time accumulated depends on the specific path taken through spacetime. This is not a metaphor. Consider the International Space Station. Its world line as it orbits Earth is nearly a straight line, a geodesic through the gently curved spacetime around our planet. But because it is moving so fast and is in a slightly different gravitational potential than we are on the surface, its geodesic is not identical to ours. The astronauts on board are following a different thread through the four-dimensional loaf. As a result, their proper time, the ticking of their clocks, very slightly outpaces our own. They age a tiny fraction of a second faster over months in orbit. This is a real, measurable difference predicted by the geometry of their world line. By learning to visualize these threads, we gain the power to predict motion and understand the flow of time from any perspective. We see that every orbit, every falling apple, and every voyage to the stars is simply an object faithfully following its assigned path through the cosmic tapestry, a path whose every twist and turn is dictated by the immutable geometry of spacetime itself. The rigid sequence of cause and effect is protected by the light cone, but our most basic assumption about time, the idea of a shared present moment, is an illusion shattered by a simple thought experiment. Picture a long train moving at a constant, high speed along an embankment. On the ground, an observer stands exactly midway between two trees. At the precise instant the center of the train passes this ground observer, two bolts of lightning strike the trees at the front and rear of the train. Because the observer is exactly in the middle, and because light travels at the same constant speed from both strikes, the two flashes of light reach their eyes at the same exact moment. For this person on the ground, the two strikes are unequivocally simultaneous. Now consider the perspective from inside the train. A passenger is sitting in the exact center of a train car. From their frame of reference, the train is at rest and the outside world is rushing past. The light from the two lightning bolts is racing toward the train. But here is the critical twist. The passenger is moving toward the light coming from the front of the train and away from the light coming from the rear. Since the speed of light is constant and does not add to the train's speed, the flash from the front has a shorter distance to travel to reach the passenger who is moving to meet it. The flash from the rear has to chase the passenger, covering a longer distance. Consequently, the passenger sees the forward flash first and the rear flash later. For the person on the train, the two strikes did not happen at the same time. The forward bolt struck first, both observers are completely correct within their own inertial frames. There is no single, privileged answer to the question of which event happened first. This is the relativity of simultaneity, a direct and unavoidable consequence of the constant speed of light. As physicist Lee Smolin puts it, simultaneity is not a fact about the world, but a relation between an event and an observer. This revelation forces us to abandon the Newtonian idea of a universal clock ticking away in a background of absolute time. There is no universal now stretching across the cosmos. The mathematical machinery that translates observations between different frames is the Lorentz transformation. These equations do not simply shift space and time coordinates independently. They mix them together. The time coordinate in one frame becomes a combination of both time and space coordinates in another frame moving relative to it. This mathematical blending is the formal expression of spacetime's unified nature. Time is not a separate, absolute river. It is a dimension woven into the fabric, and its measurement is intimately tied to your state of motion through space. This means that the slice of the universe you call your present moment is different from the present moment of someone moving relative to you. Your now and their now are not the same. Events that are simultaneous for you are sequential for them, and vice versa. This is not a perceptual trick. It is a fundamental property of reality, a necessary feature of a universe where the speed of light is the ultimate, unchangeable constant that governs the flow of information. This relativity of now dissolves the idea of a single, objective present, revealing a cosmos where every observer carries their own personal slice of time. The journey of a cosmic muon is a direct testament to time's flexibility. These unstable particles are born from violent collisions high in our atmosphere, miles above the Earth's surface. Given their fleeting lifespan, they should decay into other particles after traveling only about 600 meters, yet we detect them constantly at sea level after a journey over 10 kilometers long. The explanation lies not in their durability, but in the stretching of time itself. From our perspective on the ground, the muon's incredible velocity, a significant fraction of light speed, means its internal clock is running slow. What we measure as several microseconds of travel time might feel like only a single microsecond from the muon's own frame of reference. This time dilation allows it to survive the trip down. From the muon's point of view, it is at rest, and it is the distance to the ground that has contracted, shrinking to a length it can traverse within its short lifetime. Both descriptions are correct, revealing a universe where time is not a universal constant but a personal experience. This slowing of moving clocks is described by a precise mathematical relationship known as the Lorentz factor. It tells us exactly how much time dilates for an object in motion. The factor depends on the object's velocity relative to the speed of light. At everyday speeds like a car or a plane, the effect is vanishingly small, utterly imperceptible. But as velocity climbs, approaching that ultimate cosmic limit, the factor grows dramatically. At 87% of light speed, time is dilated by a factor of 2. A clock on that spaceship would tick half as fast as a clock on Earth. At 99.5% of light speed, time slows by a factor of 10. This is not a mechanical failure, it is a fundamental property of spacetime. A simple thought experiment, the light clock, makes this inevitability clear. Imagine a clock made from two perfect mirrors with a single photon of light bouncing between them. Each round trip of the photon constitutes one tick. Now place this clock on a spaceship moving at high speed. From inside the ship, the photon travels straight up and down. But from an external observer's perspective, the photon must travel a longer, diagonal path as the mirrors move forward. Since the speed of light is constant and absolute, the photon cannot speed up to cover this longer distance. It must simply take more time to complete each tick. The external observer sees the moving light clock ticking slower than an identical stationary clock. Crucially, this logic applies to any timekeeping mechanism, from a swinging pendulum to the vibrations of an atom or the beating of a human heart. Time itself stretches. This prediction has been verified with breathtaking precision. In 1971, physicists Joseph Haefel and Richard Keating flew atomic clocks, the most accurate timepieces ever built, on commercial airliners around the world. After the journeys, they compared these traveling clocks to others that had remained stationary at the United States Naval Observatory. The results confirmed relativity. The clocks that had flown and thus moved at high speed were slightly behind their Earth-bound counterparts. The difference was only a few hundred nanoseconds, but it matched Einstein's predictions exactly. Today, the global positioning system provides a continuous, real-world validation. If the satellites overhead did not constantly correct for the effects of both their motion and Earth's gravity, your phone's navigation would drift into uselessness within minutes. A fascinating consequence of this is its symmetry. If you are moving at a constant velocity relative to me, I will observe your clocks running slow. But from your perfectly valid frame of reference, you are at rest and I am the one moving. You will observe my clocks running slow. Each observer sees the other's time as dilated. This seems like a paradox. How can we both be younger than the other? The resolution lies not in the instantaneous observation, but in the entire history of the journey through space-time. This is the heart of the twin paradox. If one twin travels to a star and returns, the symmetry is broken. The traveling twin must accelerate to turn around, and that acceleration defines a change in inertial frames that is not symmetrical. When you map their complete world lines, the path of the traveling twin is objectively longer through the four-dimensional continuum, resulting in less accumulated proper time. They return younger. Physicist Carlo Rovelli offers a profound perspective on this, suggesting that time dilation is not an oddity, but a fundamental feature of a relational universe where time is ultimately about the interaction between things. There is no single time, only a complex web of relations. Grasping time dilation transforms our understanding of reality. It reveals that your speed through space directly trades off with your rate of time. The faster you move through the cosmos, the slower your personal clock will tick. This is the true cost of high-speed travel, not in fuel but in time itself. It is a universal rule that ensures no one can outrun their own future, a rule that becomes absolute and inescapable as we approach the final frontier, the event horizon of a black hole. That long spaceship rushing past a ground observer does not just experience slow clocks, it is physically shorter. Its very length, measured from nose to tail, contracts along its direction of flight. This is length contraction, a direct and physical consequence of the relativity of simultaneity. To measure the length of a moving object, you must note the positions of its front and back at the same exact instant. But since simultaneity is relative, a procedure that is perfectly simultaneous in one frame is hopelessly out of sync in another. From the ground observer's perspective, they record the location of the spaceship's nose and tail at a single moment in their time. For this measurement to be valid in the spaceship's own rest frame, however, those two recording events are not simultaneous. The event of marking the tail happens at a different time than the event of marking the nose. This desynchronization is what makes the object appear shorter. The mathematical formula for this contraction is the exact counterpart to time dilation. If an object has a rest length, L0, then its length L when moving at velocity v is given by L equals L0 times the square root of 1 minus v squared over c squared. Notice this is the same Lorentz factor that governs time dilation, but its effect is inverted. Time stretches out while space squeezes together. Just like time dilation, this effect is perfectly reciprocal. To the person on the ground, the high-speed spaceship is shorter, but from the window of that very spaceship, the entire Earth and its hangars are rushing past at tremendous speed, and it is the ground and all its buildings that appear compressed in the direction of motion. Both perspectives are equally valid. This reciprocity resolves the ladder paradox with elegant clarity. A farmer sees a 10-meter-long ladder moving at near light speed, length contracted to just 8 meters. She has a 10-meter barn, and for one fleeting instant she can slam both doors shut, completely enclosing the ladder inside. From the runner's frame, however, it is the barn that is moving and is therefore contracted to only 8 meters. There is no way his full 10-meter ladder can fit inside that shrunken barn at one time. The paradox dissolves when we realize the farmer and the runner do not agree on what it means for the doors to be closed at the same time. For the farmer, the front and back doors close simultaneously, trapping the entire shortened ladder. For the runner, the doors do not close at the same time. He sees the front door close first, then the ladder moves forward, and finally the back door closes after the tail has already entered. The ladder is never fully inside the barn at one single moment according to his frame. As Richard Feynman stated with characteristic directness, it is a law of physics that moving objects are shortened in the direction of motion. This is not an illusion caused by the time light takes to reach our eyes. It is a real physical contraction of space itself, a fundamental adjustment the universe makes to preserve the constant speed of light for all observers. When you combine this shrinking of space with the stretching of time, you begin to see the deep unity of spacetime. Measurements of length and duration are not independent. They are two sides of the same coin, forever trading off against one another to maintain the single, immutable reality of the spacetime interval. This intertwined nature of space and time becomes even more dramatic when we venture into a gravitational field, where the fabric of spacetime itself begins to curve. Spacetime diagrams transform the abstract mathematics of relativity into a vivid, visual map. Picture a simple grid where the horizontal direction represents space, perhaps the track of a railway, and the vertical direction represents the relentless march of time. Every event in history, from a blinking light to a cosmic collision, occupies a single point on this map, but objects are not mere points, they are stories. The continuous path an object traces through this grid is its world line. A person standing still on the platform plots a perfectly vertical line, moving forward in time but not through space. A train moving at a constant speed carves a straight, slanted world line, mixing its progress through space with its journey through time. The most critical feature on this map is the light cone. From any given event, light travels outward in all spatial directions. On our two-dimensional diagram, this traces out two lines at a perfect 45-degree angle, forming a giant X through that event. This specific angle is not arbitrary. It is the universe's signature, graphically encoding the absolute speed of light. Since light covers one unit of space for every unit of time, its path always has a slope of 1 or 45 degrees on a properly scaled diagram. This single fixed slope is the anchor of reality. Now, let us place two observers on this map. One is at rest on the platform with vertical time and horizontal space axes. The other is moving past on the train. From the platform's perspective, the train's world line is slanted. But here is the diagram's magic. For the passenger on the train, they are at rest. Their entire frame of reference is tilted relative to the platforms. On the diagram, their new time axis angles inward toward the direction of motion, and their new space axis angles as well. This simple tilt makes relativistic effects leap off the page. Time dilation becomes a matter of projection. Imagine two events that occur at the same location in the moving train, like two ticks of a clock. To the platform observer, these two ticks occur at different points in space because the train has moved between them. When the platform observer projects these events onto their own time axis, the time interval between the ticks is stretched. The clock on the train appears to run slow. Length contraction reveals itself similarly. Measuring the length of the moving train requires noting the positions of its front and back at the same instant in the platform's time. On the tilted axis of the train's frame, these two measurement events are not simultaneous. This desynchronization, when translated back to the platform's perspective, forces the train to appear shorter. These diagrams turn complex puzzles into clear geometric exercises. Consider a light signal sent from one spaceship to another. You draw the world line of the sending ship, and from a point on that line, you draw a 45-degree line representing the photon's journey. Where that light line intersects the world line of the receiving ship is the precise moment and location of reception. The constancy of the speed of light is no longer a postulate to memorize. It is the fixed diagonal line you draw with a ruler. The renowned physicists Edwin Taylor and John Archibald Wheeler insisted that students should learn to think in terms of these diagrams. In their influential textbook, Spacetime Physics, they treat the diagram not as an illustration, but as the primary language for understanding relativity. They argued that this visual intuition is more powerful than pages of algebra. This tool becomes indispensable when gravity enters the picture. In the curved spacetime around a massive star, the neat, straight grid of the diagram begins to warp. The lines representing the fabric of space and time bend and curve. The light cones, those perfect 45-degree excess, no longer stand upright. They tilt toward the source of gravity, like trees leaning in a strong wind. In simulations of a black hole, this tilt becomes so extreme that every future light cone points inward past the event horizon, graphically illustrating why nothing can escape. The diagram does not just show you that light bends, it shows you why, revealing gravity as the geometry of spacetime itself. To draw a spacetime diagram is to become a cartographer of causality, mapping the possible and the impossible on the ultimate canvas of reality. The apparent contradiction of the twin paradox cuts to the very core of spacetime thinking. Two twins are identical in every way. One remains on Earth living a quiet life. The other boards a starship, journeys to a star 10 light-years away at 80% the speed of light, and then returns. Upon reunion, the spacefaring twin is markedly younger. How can this be? If motion is relative, shouldn't each twin see the other's clock running slow? The symmetry seems perfect, the paradox undeniable, but the symmetry is an illusion. The traveling twin's journey is fundamentally different. The stay-at-home twin remains in a single, smooth, inertial frame, like a straight thread through the space-time loaf. The astronaut, however, must turn around. To reverse course and come home, the starship must fire its engines. It must accelerate. This burst of acceleration is the key that breaks the symmetrical stalemate. It is a physical sensation, a force pushing the astronaut back into their seat, a definitive signal that their state of motion has changed. During this non-inertial phase, the equivalence between the two frames is shattered. The astronaut knows unequivocally that they are the one who has changed direction. A spacetime diagram makes this resolution stunningly clear. Draw the vertical world line of the Earth twin, a straight path upward through time. Now draw the path of the traveling twin. It angles away from Earth, then, at the star, it kinks sharply, angling back to reunite with the Earth-bound twin. This is not a straight line. It is a bent, V-shaped path through the four-dimensional continuum. The true measure of time, the proper time accumulated on a clock, is the length of this world line. In the geometry of spacetime, a straight line is the longest possible path between two events in terms of proper time. The Earth twin on the straight path experiences the most time. The traveling twin on the shorter, kinked path simply experiences less duration. Their life thread is literally shorter. We can calculate this using the invariant spacetime interval. For the Earth twin, the entire journey happens in one place, so their elapsed proper time is simply the time measured on Earth. For the traveling twin, their path involves huge movements through space, which subtracts from the accumulated time in the interval equation. The result is less proper time, a younger twin. While the intense acceleration at the turnaround does involve general relativity, the core effect is from special relativity. If we model the turnaround as an instantaneous, infinitely sharp kink in the diagram, the calculation still holds. The acceleration simply marks the point where the traveler switches from one inertial frame to another. As physicist Paul Davies concluded, the twin paradox is not a paradox at all once you consider the entire spacetime geometry. The universe is not ambiguous about this. Elapsed time is not a universal constant. It is a personal odometer reading that depends entirely on the path you take through the cosmos. Your journey writes your own time. Could you send a message to your younger self and tell them to avoid a terrible mistake? This tantalizing idea of changing the past is the ultimate fantasy, but it is also a fundamental impossibility enforced by the light cone. The entire structure of spacetime is designed to prevent paradoxes, to ensure that a cause always comes before its effect. If you could travel faster than light, you could chase after a photon that left Earth years ago, overtake it, and arrive at a distant star before the light from your own birth had even reached it. From that star, you could then send a signal that would arrive on Earth before you ever left. You could become your own ancestor or prevent your own birth, creating a logical contradiction that would unravel reality itself. This is why the universe imposes its ultimate speed limit. The light cone is the guardian of causality. Any event that could possibly influence your present must lie within your past light cone. Any event you can affect must lie within your future light cone. The slope of that cone is fixed by the speed of light. If you could move faster than light, you could escape the confines of your future light cone and enter the region of elsewhere, a domain that, from your original perspective, is in your own past. Your world line would loop back on itself, forming what physicists call a closed time-like curve, a path through spacetime that visits its own history. The order of events that are causally connected, linked by a signal traveling at or below light speed, is sacred. All observers, no matter their state of motion, will always agree that the cause happened before the effect. For events that are space-like separated, however, out in the elsewhere, different observers can disagree on the sequence. One might see event A before B, another might see B before A. This is perfectly safe because these events cannot influence each other. No signal can be sent between them, so the reversed order creates no paradox. It is merely a matter of perspective. This is why hypothetical particles called tachyons, which would always travel faster than light, are generally considered unphysical. If they existed, they could be used to send information into the past. A clever arrangement of tachyonic transmitters could create a scenario where a message is received before it is sent, directly violating causality. The universe seems to have a deep-seated rule against this. even in the realm of general relativity and its most extreme solutions like wormholes, causality is protected. Theoretical physicist Kip Thorne and his colleagues explored the idea of a traversable wormhole, a shortcut through spacetime. If one end of the wormhole was moved at high speed and then brought back, time dilation would cause the two mouths to be out of sync. You could jump into the moving mouth and exit the stationary one at a time before you entered. This would be a time machine, but Thorne's work also showed that such a setup would likely be unstable. The mere attempt to use it to create a paradox like going back to kill your grandfather would trigger a physical reaction, such as a wall of intense energy or the collapse of the wormhole itself, preventing the contradictory event from occurring. It seems the laws of physics have a built-in censorship, a cosmic veto against logical inconsistency. Upholding causality is not just a convenient rule. It is the foundation of a coherent, predictable universe where effects follow causes and our actions have meaningful consequences. The light cones are the silent, immutable sentinels that guard the flow of time, ensuring that the past remains written and the future remains open to our choices. Einstein's great leap was to realize that gravity is not a force in the usual sense. It is the shape of spacetime itself. Imagine a taut, flexible rubber sheet representing the fabric of spacetime. Place a heavy bowling ball in its center. The sheet sags, creating a deep, smooth depression. Now, roll a marble across this warped surface. Instead of traveling in a straight line, the marble curves, orbiting the heavy mass in a graceful arc. It is not being pulled by a mysterious force. It is simply following the most direct path available through the curved geometry. This is the essence of general relativity. Mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. The mathematical engine that describes this beautiful, dynamic relationship is the Einstein field equations. These are not simple formulas. They are a set of 10 interlinked differential equations that precisely relate the geometry of spacetime on one side to the energy and momentum of matter on the other. They are the universe's own instructions for how content creates form. One of the first and most dramatic confirmations of this idea was the bending of starlight. If the sun's mass curves the spacetime around it, then a light ray from a distant star grazing the sun's edge should be deflected from a straight path. Arthur Eddington led an expedition to observe a total solar eclipse in 1919. With the sun's light blocked, they could photograph the stars appearing near its darkened disk. The measured positions of those stars were shifted, exactly as Einstein's equations predicted. Starlight itself was falling into the sun's gravitational well. A second key prediction is gravitational time dilation. The deeper you are in a gravitational field, the slower your clock will run. A clock at sea level, closer to Earth's mass, ticks more slowly than an identical clock on a mountaintop. This is not a mechanical effect. It is time itself stretching under the influence of gravity. Your head ages faster than your feet by a tiny but real amount. This effect is crucial for the GPS satellites we rely on. Their clocks, in a weaker gravitational field high above Earth, run faster than ours, and this must be precisely calculated and corrected for the system to work. These predictions are profound, but they are gentle whispers compared to the cosmic shout of a black hole. A black hole is a region where so much mass is compressed into such a small volume that spacetime curvature becomes infinite. The depression in our rubber sheet becomes a bottomless pit. At the boundary of this pit, the event horizon, the curvature is so extreme that the future light cone of any object tilts completely inward. Every possible path, even for light itself, leads downward into the singularity. There is no future left that points outward. nothing, not even information, can escape. This is the ultimate expression of thinking in curved spacetime. As the physicist John Wheeler so elegantly summarized, spacetime tells matter how to move, matter tells spacetime how to curve. General relativity reveals that our mental map of the universe must be drawn not on a flat, static grid, but on a dynamic, malleable fabric that breathes and bends with the mass and energy within it. The event horizon of a black hole is the final point of no return. It is not a physical surface you can touch, but a mathematical boundary in space-time, a one-way membrane where the escape velocity precisely equals the speed of light. Cross this invisible threshold, and the universe as you know it ceases to be your home. All possible futures, every path that matter, energy, or information can take, now point relentlessly toward the central singularity. The light cone, that perfect architecture of possibility, has tipped over completely. From an outside observer's perspective, a clock falling toward this horizon would appear to tick slower and slower, freezing completely at the edge. The light from the falling object would redshift into an infinite, undetectable wavelength, fading from view as if consumed by the ultimate silence. This is the cosmic stage for one of physics' greatest dramas. As Stephen Hawking theorized, black holes are not entirely black. Quantum effects near the event horizon allow them to radiate energy, slowly evaporating over astronomical timescales. This Hawking radiation creates a profound puzzle, the information paradox. If a black hole evaporates completely, what happens to all the information about the objects that fell in? Quantum mechanics insists information cannot be destroyed, yet general relativity suggests it is lost forever inside the singularity. Hawking himself wrestled with this, famously stating that black holes have no hair, meaning they conceal all details of what formed them, but his later work suggested information might somehow be preserved, a mystery that remains unresolved. The journey toward the singularity is a violent one. Long before you reach the center, tidal forces take over. Imagine falling feet first toward a stellar mass black hole. The gravitational pull on your feet is vastly stronger than the pull on your head. You would be stretched lengthwise into a long, thin stream of atoms, a process grimly known as spaghettification. Simultaneously, the sides of your body would be compressed inward, as if by a cosmic vise. These are not forces in the traditional sense, but the direct result of the extreme curvature of spacetime, a gradient so steep it pulls different parts of your body in different directions with ferocious strength. We can visualize this entire bizarre landscape using a Penrose diagram. This clever map compresses the infinite distances of spacetime into a finite picture, allowing us to track the paths of light rays and the boundaries of causality. On such a diagram, the event horizon appears as a 45-degree line, the point where all future light cones tilt irrevocably inward. The singularity is drawn as a jagged line representing the end of time itself for anything that crosses the horizon. Light rays that approach the black hole from outside are bent, their paths curving sharply. Those that skim the horizon get trapped in orbits, defining the photon sphere, a region where light can circle the black hole forever, until the slightest disturbance sends it either spiraling inward or flying off into space. Black holes represent the ultimate victory of gravity, where the warping of spacetime becomes so absolute that it rewrites the fundamental rules of cause and effect, creating a region of the universe where the future is not just predictable, but inescapably singular. Your phone's navigation is a daily miracle of gravitational time dilation. The atomic clocks on those GPS satellites orbiting far above Earth do not tick at the same rate as the clocks in your device. They run faster, gaining about 38 microseconds each day. This is not a design flaw. It is a direct prediction of general relativity, confirmed with every turn-by-turn direction. A clock in a weaker gravitational field, farther from a massive body, simply ticks faster than a clock trapped deep within a gravity well. Einstein himself stated that the rate of a clock is influenced by the gravitational potential at its location. Picture two identical clocks, one placed on the floor and another on a high shelf. The clock on the floor, experiencing a slightly stronger gravitational pull, will lag ever so slightly behind the clock on the shelf. Its time is stretched, its rhythm slowed by the gravity well. This effect is mathematically described by a formula that ties the slowing of time directly to the gravitational potential. The closer you are to a source of gravity, the more your personal time expands, the slower your clock appears to run from a distant vantage point. This gravitational time dilation works in concert with the velocity-based time dilation from special relativity. For the GPS satellites, the velocity effect makes their clocks run slow, while the gravitational effect makes them run fast. In their case, gravity wins, resulting in that net gain of 38 microseconds. If engineers did not deliberately pre-adjust the satellite clocks to compensate, your mapped location would drift by over 10 kilometers per day, leaving you utterly lost. This is not just theory, it has been verified with exquisite precision. In the Pound-Rybka experiment, physicists measured the tiny frequency shift of gamma rays falling down a tower at Harvard University. As the light fell deeper into Earth's gravity well, it gained energy, and its frequency shifted exactly as general relativity predicted. More simply, comparisons of ultra-precise atomic clocks placed at different altitudes, on mountains versus in valleys, confirm that elevation alone changes the passage of time. Your head is physically aging faster than your feet, by a minuscule but real amount. This flexibility of time is woven into the fabric of the cosmos, a fundamental feature of living in a universe where spacetime is curved by mass and energy. Grasping this concept transforms our understanding of time from a rigid metronome into a fluid, personal experience, deeply connected to our place in the gravitational landscape of the universe. The raisins are not rushing away from each other, the dough between them is simply rising. This is the most powerful analogy for our expanding universe. Galaxies are not flying through a static space like projectiles. They are largely at rest within the fabric of spacetime itself, and it is that fabric that is stretching, carrying the galaxies apart as it grows. The farther apart two raisins are, the more dough expands between them, and the faster they appear to recede from one another. This is the essence of Hubble's law, a direct relationship between a galaxy's distance and its velocity of recession. A galaxy twice as far away is moving away twice as fast. We see this written in the light from distant galaxies, not as a Doppler shift from their motion through space, but as a cosmological redshift. The very waves of light are stretched to longer, redder wavelengths during their multimillion-year journey to us, because the space through which they travel is expanding en route. This is not a trivial distinction. It means the universe itself is dynamic, evolving, and has a history. The mathematical engine that describes this cosmic evolution is governed by the Friedmann equations, derived from Einstein's theory of general relativity. These equations tell us how the scale of the universe changes over time, dictating its ultimate fate based on its density and composition. They reveal a cosmos that was once unimaginably hot and dense, and has been cooling and expanding ever since. This expansion fundamentally reshapes causality on the grandest scales. Every galaxy has its own observable universe, a spherical region bounded by what cosmologists call the particle horizon. This horizon is not a physical wall. It is the ultimate limit of our knowledge, the distance that light has had time to travel since the beginning of the universe, some 13.8 billion years ago. We cannot see anything beyond this horizon, not because it is too dark, but because the light from those regions has not had enough time to reach us yet. The events occurring out there are, for now, permanently in our elsewhere, causally disconnected from our entire history. To explain the remarkable uniformity of the cosmos we see in all directions, physicists like Alan Guth proposed a breathtaking mechanism called inflation. In the first fleeting fraction of a second after the Big Bang, the universe is thought to have undergone a period of exponentially rapid expansion, smoothing out any initial wrinkles and setting the stage for the slower, more steady expansion we observe today. This initial growth spurt stretched the primordial spacetime fabric so dramatically that it locked in a uniformity that would otherwise be inexplicable. As the cosmos expands, the light cones of distant galaxies are pulled taut. Their future light cones, which define all they can ever hope to influence, are stretched over ever greater volumes of space, while their past light cones, which contain their entire causal history, are drawn from an increasingly vast and ancient realm. This means that galaxies now passing beyond our horizon were once within it, and are now forever fading from view, their light too redshifted to ever detect again. The expanding universe is not just a fact about distant galaxies. It is the story of spacetime itself, a living, breathing entity that dictates what we can see, what we can know, and what parts of the cosmos will forever remain beyond the reach of our influence. Our cosmic address has a final, absolute limit. We live inside a vast but finite sphere called the observable universe, and its boundary is known as the particle horizon. This is not a wall you could crash into. It is the ultimate edge of our knowledge, the maximum distance from which light has had time to reach us since the dawn of time, the Big Bang. Every photon that arrives at our telescopes, from the closest star to the faintest galaxy, originated from inside this sphere. Beyond it, the universe does not end, but its light is still in transit, or due to the expansion of space, may never reach us at all. This creates a companion boundary in our future, the cosmic event horizon. While a black hole's event horizon is a point of no return for anything falling in, our cosmic event horizon is a point of no return for light coming out. It defines the future boundary beyond which any event occurring today will forever be invisible to us. The accelerating expansion of the universe, driven by the mysterious force of dark energy, means that distant galaxies are being carried away from us so quickly that the light they emit now is traveling through an ever-widening gulf of space. That light is fighting a losing battle against the stretching fabric, destined to never arrive. This entire drama is mapped by our light cones in an expanding spacetime. Our past light cone stretches all the way back to the Big Bang, defining our particle horizon. Our future light cone, however, is progressively truncated by the accelerating expansion, defining our event horizon. Distant galaxies that we see today are still within our past light cone, but they are steadily moving across its boundary into the causal elsewhere. We must distinguish this from the Hubble sphere, the distance at which a galaxy's recession velocity equals the speed of light. Due to the expansion, the particle horizon is actually farther out than the Hubble sphere. We can see galaxies that are technically receding from us faster than light, because the light we see today was emitted long ago when they were much closer and space was less stretched. But for any light those galaxies emit today, the space between us is now expanding too quickly for it to ever cross the gap. As physicist Max Tegmark noted, our cosmic horizon defines the ultimate limit of our knowledge. This has a profound implication for causality. Every patch of the cosmos beyond our particle horizon is causally disconnected from us, since no signal, not even light, has had time to travel between us since the beginning. These regions have never been in contact. They could, in principle, have entirely different physical properties, different constants of nature, even different histories, without creating any logical conflict. There is no law of physics that requires the entire universe to be uniform, only the part that has been in causal contact. Our observable universe is just one island of causality in a possibly infinite and vastly diverse cosmic archipelago. The light cones that once connected us to distant galaxies are being stretched to their breaking point, severing the threads of causality one by one, and reminding us that our view of the cosmos is not only finite but also fleeting. A wormhole is a theoretical bridge, a secret passageway through the folded fabric of spacetime. Imagine the universe as a vast sheet of paper with two distant points marked on it. Instead of traveling the long way across the surface, a wormhole proposes a shortcut, a tunnel that punches through the paper's higher dimensions, connecting those points in an instant. This is not just faster than light travel, it is a rewriting of the cosmic map. Such a structure, if stable, would not only connect distant places but different times. A journey through one mouth could, under the right conditions, deposit you into your own past. But keeping this tunnel open against the crushing force of its own gravity requires something truly bizarre, exotic matter. This is not merely strange matter, but a substance with negative energy density, something that gravitationally repels rather than attracts. It is the only thing that could act as a kind of cosmic scaffolding, propping the wormhole's throat open against collapse. The theoretical blueprint for such a structure is the Morris-Thorne wormhole, a specific solution to Einstein's field equations that describes a traversable tunnel. Within the warped geometry of such a wormhole, the light cones, those guardians of causality, can be twisted. If one end of the wormhole is moved at high speed and brought back, time dilation would cause the two mouths to be out of sync. Your entrance into the moving mouth might become an exit from the stationary mouth at a time before you even left. The path you followed, your world line, would now be a closed time-like curve, a loop in spacetime that revisits its own history. This is the gateway to the ultimate paradox. Could you go back and prevent your own birth? Physics might have a built-in safeguard against such logical nightmares, the Novikov self-consistency principle. This idea suggests that the laws of physics simply will not allow a paradox to happen. Any attempt to create an inconsistency, like the famous grandfather paradox, would be thwarted by seemingly random events. Your gun would jam, you would slip on a banana peel. Some small, unforeseen occurrence would always intervene to ensure the timeline remained consistent. Your free will to change the past would be an illusion, constrained by the immutable logic of a single, self-consistent history. At an even deeper level, quantum mechanics may slam the door shut entirely. The intense, fluctuating energies at the wormhole's throat might naturally trigger a feedback effect that destroys the tunnel the instant it becomes traversable. The vacuum of space itself, seething with virtual particles, could destabilize the exotic matter, causing the wormhole to collapse into a singularity before any information could pass through. This speculative physics was popularized in the film Interstellar, where a wormhole near Saturn serves as a gateway to distant worlds. While the movie took artistic license, its scientific consultant, Kip Thorne, grounded its visuals in real general relativity. Thorne himself stated, "Wormholes are a theoretical possibility, but whether nature allows them is an open question. We have never observed one, and the required exotic matter remains purely hypothetical." Exploring these cosmic shortcuts is less about planning a vacation through time and more about probing the absolute limits of our physical theories. They stretch our imagination of spacetime's possible geometries, forcing us to ask if the universe's laws are merely rules for the game, or if they are the unbreakable walls of the arena itself. The smooth, deterministic fabric of spacetime meets its strangest challenge in the quantum realm. Down at the smallest scales, particles exist in a ghostly state of multiple possibilities, a superposition, only settling into a single reality when we observe them. This is the infamous measurement problem, and it creates a direct conflict with Einstein's graceful picture of curved spacetime. How can a reality built on fuzzy probabilities create the sharp, definite geometry of general relativity? This clash becomes spectacularly apparent at the edge of a black hole, in the information paradox. Quantum mechanics insists that information about what falls into a black hole can never be truly lost, yet general relativity suggests it is irretrievably crushed in the singularity. Both theories are profoundly successful, but they cannot both be completely right in such extreme conditions. To resolve this, we must look at how quantum fields paint reality. Quantum field theory tells us that particles are not tiny grains of sand. They are localized vibrations, tiny excitations, in invisible, all-pervasive fields that fill every corner of spacetime. The electron field vibrates to create an electron, the quark field for a quark. Even in what we call empty space, these fields are never truly quiet. The Heisenberg uncertainty principle allows for a constant, seething dance of virtual particles. These are particle-antiparticle pairs that borrow energy from the vacuum, popping into existence for an unimaginably brief moment before annihilating each other and returning the energy. This quantum jitter is not just a mathematical curiosity. It has real, physical effects. These fleeting virtual particles carry energy, and energy curves spacetime according to Einstein's equations. The vacuum itself, therefore, has a gravitational pull, a cosmological constant that drives the accelerating expansion of the universe. This is where the quest for a unified theory begins. How do we make the smooth, classical geometry of spacetime itself subject to the fuzzy, probabilistic rules of quantum mechanics? Two leading paths have emerged, each with a radically different vision. String theory proposes that the fundamental objects are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrational modes of these strings give rise to all the different particles we see, and gravity, with its spacetime curvature, emerges naturally from the theory. It suggests spacetime may have many more than 4 dimensions, most of them curled up into a size too small to detect. The other major approach, loop quantum gravity, takes a more direct route. It proposes that spacetime itself is not a smooth continuum, but is woven from a fabric of tiny, discrete, finite loops. Think of it as a cosmic polymer with a smallest possible unit of space and time. This granular structure would prevent the singularities predicted by classical general relativity, offering a natural endpoint for the collapse of a black hole. Meanwhile, quantum entanglement adds another layer of profound weirdness. Two particles can become linked or entangled, such that measuring the state of one instantly determines the state of the other, no matter the distance separating them. Einstein called this spooky action at a distance, yet this spookiness does not violate the light cone's law. While the correlation is instantaneous, it cannot be used to send any meaningful information faster than light. The outcome of any measurement is random and uncontrollable, so no signal, no cause and effect can jump the gap. Causality remains perfectly safe. Some physicists, like Roger Penrose, believe the solution to the measurement problem lies at this very intersection. He proposes that the sheer mass of an object, and thus its gravitational influence, causes its quantum superposition to spontaneously collapse into a single state. In this objective collapse theory, gravity itself is the trigger that forces the quantum world to make up its mind, bridging the gap between the tiny and the cosmic. The ultimate nature of spacetime, it seems, is waiting for its own theory of the quantum to be fully revealed. Einstein's own words reveal a startling vision of reality. In a letter of condolence to the family of his lifelong friend Michel Besso, he wrote, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. This is the block universe, a model where the entire timeline of existence is laid out at once, a single, unchanging four-dimensional sculpture. Your birth, your reading of this sentence, and every moment to come already have their place in this cosmic structure, just as fixed as the spatial distance between two stars. In this view, the flow of time is a powerful, convincing trick of our consciousness, a mental slide projector illuminating one frame after another in a film that is already complete. Since relativity abolishes a universal now, declaring that your present moment is not the same as someone else's moving past you, the only objective reality is the entire block, the whole film strip from beginning to end. Your world line is not being drawn as you live. It is a permanent thread in the tapestry, its entire path from start to finish already woven into the fabric of spacetime. This feels deeply wrong to our lived experience. We feel we are moving into a future that is open and undecided. Yet, the block universe suggests that free will might be as illusory as time's flow. Are we merely passengers on a train ride, reading a story whose pages are already written, even though we do not know the ending? This deterministic picture faces a formidable challenge from the quantum world. Quantum mechanics is built on probability and inherent randomness. Until a particle is observed, it exists in a haze of many possible states, a superposition. Its properties are not fixed until the moment of measurement. How can this fit into a block universe where every event is predetermined? If the outcome of a quantum experiment is genuinely random, not just unknown, then the future may not be written after all. Perhaps the block is not a static carving but a growing one, where new events are constantly crystallizing from a fog of possibility. This is the heart of a fierce debate in physics. Philosophers and scientists who hold the presentist view argue fiercely against the block. They insist that only the present moment is real. The past is gone, a set of memories and records, and the future is pure potentiality. It does not yet exist. For them, the relativity of simultaneity does not destroy the reality of the now. It just means that each observer has their own unique present. They see the block universe as a mathematical abstraction that ignores the most immediate fact of our existence, the palpable sensation of becoming. So which is it? Is our lives a journey along a pre-existing path, or are we actively writing the story with every choice? The block universe forces us to confront the very nature of reality. It asks whether time itself is a fundamental property of the cosmos, or merely a way our brains organize a sequence of events that are all equally real. Perhaps the truth lies in a synthesis we have not yet discovered, a theory that unites the timeless geometry of spacetime with the unpredictable jitter of the quantum world. Until then, we are left with a profound choice about how we see our own place in the cosmos, navigating the tension between a universe that seems complete and a life that feels open. That subtle lag in your phone's navigation is a whisper from Einstein himself. The entire global positioning system is a symphony of relativistic corrections playing out in real time above our heads. Each satellite carries an atomic clock of breathtaking precision, but these clocks would drift into uselessness without accounting for both special and general relativity. Their high orbital speed causes their clocks to tick slower than ours on the ground, a special relativistic effect. Simultaneously, because they are farther from Earth's mass, their clocks tick faster due to gravitational time dilation. These two effects don't cancel. The gravitational effect wins, causing the satellite clocks to gain about 38 microseconds each day. If engineers did not deliberately program these clocks to run slow before launch, your mapped location would drift by over 10 kilometers every single day. This is not a theoretical adjustment. It is a daily, practical necessity baked into the very code that guides you. One engineer working on the system put it bluntly: without relativity, GPS simply would not work. The financial markets and power grids that synchronize their operations using these satellite signals would also falter, their precise timing thrown into chaos. This same precise timekeeping is crucial for particle accelerators like the Large Hadron Collider. Here, protons are whipped to 99.9999991% of the speed of light. At these velocities, their mass increases dramatically due to relativistic effects. The powerful magnets that steer these beams must be designed with this increased mass in mind. Otherwise, the particles would not follow their intended path, and the carefully orchestrated collisions would never happen. The energy of each collision, the key to discovering new particles, is also a calculation straight from Einstein's playbook, relying on the full relativistic relationship between energy, momentum, and mass. Even medical imaging depends on this spacetime thinking. A PT scan or positron emission tomography tracks a radioactive tracer in your body. As this substance decays, it emits positrons, which are the antimatter counterparts to electrons. When a positron meets an electron, they annihilate each other, converting their mass directly into energy and producing two gamma rays that fly off in opposite directions. The detectors in the scanner rely on the fact that these two gamma rays are emitted at nearly the speed of light. Relativistic kinematics are essential for calculating their paths and pinpointing the exact location of the annihilation event within your body, creating a detailed image of metabolic activity. From guiding your car to probing the fundamental building blocks of matter and peering inside the human body, the principles of spacetime are not abstract curiosities. They are the invisible foundation of our modern technological world, solving real-world problems with a precision that would be otherwise impossible. Albert Einstein placed imagination above knowledge for a very specific reason. Knowledge describes the world as we have found it, but imagination allows us to tear down the walls of common sense and see the universe as it truly is. This is the power of the thought experiment, a mental gymnasium where you can train your intuition for the strange realities of space-time. You do not need a laboratory or complex equations, just a willingness to follow a scenario to its logical and often astonishing conclusion. One of the most elegant is Einstein's own light clock. Picture a clock made from two perfect mirrors with a single photon bouncing between them. Each round trip is one tick. Now place this clock on a moving train. For a passenger on the train, the photon travels straight up and down. But for you, standing on the platform, the story is different. You see the photon travel a longer, diagonal path as the clock moves forward. Since the speed of light is absolute and cannot change, the only possible outcome is that the moving clock must tick slower. This simple image makes time dilation feel inevitable, a direct consequence of light's constant speed. You can apply this same logic to any clock, from a swinging pendulum to your own heartbeat, proving that time itself stretches for moving objects. Another classic experiment forces us to confront the relativity of simultaneity. Imagine a train car moving past an embankment. Two bolts of lightning strike the ground at the same instant, one at the front of the train and one at the rear, and an observer on the ground, perfectly positioned in the middle, sees the flashes arrive simultaneously. But what about a passenger sitting in the exact center of the train car? From their perspective, they are moving toward the light from the front and away from the light from the rear. The forward flash reaches them first. For them, the strikes were not simultaneous at all. The thought experiment walks you through the steps, defining the scenario, applying the principle of constant light speed, and then reconciling the two perfectly valid but conflicting observations. There is no single correct answer to the question of which bolt struck first. The universe itself refuses to declare a winner. To grasp the extreme curvature of space-time, try visualizing a fall toward a black hole. You are not being pulled down by a force, you are simply following the straightest possible path through a deeply warped geometry. As you approach the event horizon, the future light cones tilt so drastically that every possible path leads inward. Looking out, you would see the entire history of the universe play out in a final, blinding flash of light, while to any outside observer, your own image would slow, redden, and fade to black, frozen forever at the point of no return. Modern variants of these exercises push into quantum territory, like the thought experiment of quantum suicide. It proposes a scenario where a device is triggered by the decay of a radioactive atom, an event governed by quantum probability. In one outcome, the device activates and ends the experiment. In another, it does not. The unsettling suggestion is that from the perspective of the observer within the experiment, they only ever experience the branches of reality where they survive, leading to a kind of immortality in a multiverse. While speculative, this idea challenges our deepest assumptions about causality and the nature of a single, objective reality, forcing us to ask where the boundaries of space-time thinking truly lie. The true value of these mental exercises is not in finding a definitive answer, but in the process itself. They rewire your brain to question assumptions you never knew you had, to see motion, time, and causality not as fixed absolutes, but as dynamic relationships within a four-dimensional whole. By practicing them, you are not just learning about relativity, you are learning to think in its native language, building an intuition for a world where the fabric of reality is as flexible and surprising as your own imagination. Your personal measurement of the world is not a passive recording, it is an active creation. In the universe of relativity, you are not a spectator watching a fixed play on a stage. You are a performer whose very motion dictates the rhythm of the scenes and the spacing of the props. What you record as a meter of length or a second of duration is intimately tied to your state of motion and your place in a gravitational field. This makes every observer a co-author of reality, each writing a slightly different yet equally valid chapter of the same cosmic story. We have already seen how two honest witnesses can disagree on whether two lightning strikes were simultaneous or whether a ladder fits inside a barn. There is no single God's eye view that can declare one perspective true and the others false. The farmer and the runner, the passenger and the platform god, all inhabit their own genuine realities. Yet beneath this kaleidoscope of perspectives lies a bedrock of absolute agreement. While observers may quarrel over times and distances separately, they will all unanimously agree on the space-time interval, that fusion of space and time into a single, immutable measure. It is the true distance between two events in the four-dimensional fabric, a fundamental fact that remains constant for everyone. This is the hidden harmony within the apparent chaos, the common ground that ensures we all still share the same universe even as we experience it differently. This profound role of the observer echoes into the quantum realm, where its influence becomes even more startling. In quantum mechanics, a particle exists in a haze of many possible states, a superposition, until a measurement is made. The act of observation itself seems to force this cloud of possibilities to collapse into a single, definite outcome. The observer here is not just measuring reality, but participating in its very manifestation. This has led to intense debates as physicists struggle to merge the smooth, deterministic geometry of general relativity with the fuzzy, probabilistic nature of quantum mechanics. How can a reality built on observation-dependent facts create the solid, continuous spacetime we experience? The philosopher of science Thomas Kuhn offered a powerful lens for understanding such scientific revolutions. He argued that science does not progress by simply adding new facts to an old framework. Instead, it undergoes paradigm shifts where the entire conceptual worldview, the set of questions deemed meaningful, changes fundamentally. Adopting the spacetime view is such a shift. It requires letting go of the deeply ingrained idea of a universal now and accepting that your perspective is woven into the very fabric of what you see. Recognizing the active role of the observer is not a descent into subjectivity, but an ascent to a deeper understanding of the relational nature of the cosmos. Your reality and mine are different threads in the same tapestry, each valid, each essential, and all bound together by the unbreakable geometry of spacetime. Our everyday intuition is a powerful but flawed guide to reality. We evolved in a world of walking speeds and gentle gravity, a domain perfectly described by Isaac Newton's laws. In that familiar realm, time is a universal river flowing at the same rate for everyone, and objects have fixed lengths. This is the physics that feels true, the common sense that tells you a moving train is objectively in motion. Yet this intuition is a local guide, useless for navigating the cosmic highways of spacetime. Our brains are simply not wired to naturally accept that your now and my now can be different slices of the universe. This is the first and greatest barrier to spacetime thinking. One major cognitive hurdle is our inability to truly visualize 4 dimensions. We can easily picture a 3-dimensional object, but adding time as a 4th dimension stretches our imagination to its breaking point. We try to visualize it as a movie, but a movie is just a sequence of 3-dimensional moments. Grasping the entire 4-dimensional loaf of existence as a single, static structure, as the block universe suggests, feels alien and deeply counterintuitive. Another stubborn misconception is the belief that if motion is relative, then everything must be relative. This is not true. While measurements of space and time are relative to an observer's frame, certain things are absolute and agreed upon by everyone. The speed of light in a vacuum is the ultimate constant. The spacetime interval between 2 events is an immutable fact. Causality, the unbreakable rule that cause precedes effect, is preserved for all observers. The universe has a rigid backbone of absolutes that prevent it from dissolving into a chaos of individual perspectives. People also often mistake time dilation for a mere illusion of perception, a trick of the light. It is not. If a cosmic muon survives its journey to the ground, it is not because it appears to live longer from our point of view. Its internal processes, from the decay of its particles to the ticking of any hypothetical clock, are physically slower. The effect is real, measurable, and has been confirmed with ultra-precise atomic clocks on airplanes. The twin who travels to the star and back is genuinely, physically younger than their sibling. Their threads through spacetime have different lengths. This is why even brilliant physicists can find these concepts challenging. Richard Feynman once remarked about the equally bizarre quantum mechanics. I think I can safely say that nobody understands quantum mechanics. A similar, though perhaps less absolute, mystery surrounds relativity. We can use the mathematics, we can predict the outcomes with stunning accuracy, but fully internalizing a reality where time is personal and space is malleable is a lifelong endeavor. The path to mastery lies in retraining your intuition. This is where powerful tools like analogies and spacetime diagrams become essential. The loaf of bread or the film strip for the block universe gives you a tangible handle on a four-dimensional concept. The spacetime diagram, with its light cones and world lines, turns abstract algebra into a visual map you can explore. When you struggle with a paradox, do not try to force it into a three-dimensional mindset. Draw it, map the events on a diagram, and follow the world lines. You will see the resolution emerge from the geometry itself. Embracing this discomfort is not a sign of failure. It is the essential first step in learning to see the world as it truly is, not just as our earthbound senses report it. This journey rewires your brain, replacing a narrow, local intuition with a cosmic one, granting you the profound ability to think in spacetime. A universe that expands faster every day defies our deepest expectations. The mysterious force driving this acceleration, dark energy, remains the single greatest puzzle in cosmology. We know it makes up about 70% of the cosmos, but we do not know what it is. Is it the energy of the vacuum itself, a cosmological constant Einstein once imagined? Or is it a dynamic field that changes over time, a new kind of cosmic fluid? The answer will dictate the ultimate fate of everything, determining whether the universe expands forever into a cold, dark emptiness or eventually reverses course. This mystery is linked to another profound frontier, the black hole information paradox. Stephen Hawking's calculation that black holes evaporate seems to suggest that all the information about what fell in is lost forever, a direct violation of quantum mechanics' core tenet that information cannot be destroyed. Leonard Susskind and others have fought this idea for decades, leading to radical proposals like the holographic principle. This principle suggests that our three-dimensional reality, including everything that falls into a black hole, might be entirely encoded on its two-dimensional event horizon, like a cosmic DVD. The information is not lost, it is just stored in a way we do not yet fully understand. As physicist Juan Maldacena demonstrated with his groundbreaking work on the AD/CFT correspondence, a gravitational theory in a warped spacetime can be perfectly equivalent to a quantum field theory without gravity on its boundary. This hints that spacetime itself may not be fundamental, but instead emerges from a vast, entangled network of quantum information. The ultimate goal is to weave these threads into a single, coherent theory of quantum gravity, a framework that can describe the frantic jitter of the quantum world and the smooth curvature of spacetime as one unified reality. String theory proposes that the fundamental constituents are tiny, vibrating strings, and that gravity emerges from their dance in a universe with many hidden, curled-up dimensions. Theorist Lisa Randall explores how these extra dimensions might influence the cosmos on the largest scales. The alternative path, loop quantum gravity, suggests spacetime is not smooth but composed of discrete, finite loops, a fabric woven from individual threads. These are not just abstract ideas. A new generation of experiments is being built to test them. The Laser Interferometer Space Antenna, or LISA, is a planned space-based observatory that will detect gravitational waves from the mergers of supermassive black holes. By listening to the ripples in spacetime from these colossal events, we could probe the very nature of gravity and the structure of spacetime near black hole horizons. Other experiments search for subtle imprints of the early universe, looking for signs that our cosmos is just one bubble in a vast multiverse, each with its own unique laws of physics. These are not questions for a distant future. They are the burning issues driving theoretical physics today, pushing us toward a revolution that may reveal spacetime to be a secondary, emergent property of a deeper, more fundamental reality we are only beginning to glimpse. Rewiring your brain for spacetime begins with a pencil and paper. Sketch a simple spacetime diagram for your morning commute. Draw a vertical line for time and a horizontal line for space. Your home is a vertical world line since you are at rest. Now draw your trip to the store as a slanted line moving away from home, and your return as another slanted line coming back. Where the lines bend is your acceleration the moment you turn the car around. This simple act of mapping your daily life onto a two-dimensional grid is the most powerful first step. It transforms an abstract concept into a tangible map of your own existence. You can then play with this diagram. What if you traveled to the store at near light speed? Your world line would be much flatter, closer to the 45-degree angle of light, and the distance to the store would contract on your personal map. Free apps and online simulators let you experience this distortion directly. You can pilot a virtual spaceship and watch as the stars ahead blue shift and the universe behind you compresses into a tunnel of light. These tools make the bizarre consequences of relativity feel visceral and real, not just theoretical. Your next step is to immerse yourself in the stories of spacetime. Read popular science books by authors like Brian Greene or Carlo Rovelli, who have a gift for weaving clear narratives from complex ideas. Watch documentaries that use cutting-edge graphics to visualize curved space around black holes or the expansion of the cosmos. The goal is not to memorize equations, but to absorb the imagery and the logical flow of the arguments. Then, take these ideas to an online community or a discussion group. Trying to explain the twin paradox to someone else is one of the best ways to uncover the gaps in your own understanding. You will find that the collective effort to solve a relativistic puzzle sharpens your intuition far more than solitary study ever could. Begin your mental training with the clean, sharp puzzles of special relativity. Master the train and lightning thought experiment until the relativity of simultaneity feels inevitable, not just strange. Grapple with the ladder paradox until you can confidently draw the spacetime diagram that resolves it from both perspectives. Once these foundations are solid, introduce gravity. Use the classic rubber sheet analogy for general relativity, but push it further. Imagine how a rolling marble's path is the straightest possible line on that curved surface. Finally, when you are comfortable with curved spacetime, dip your toes into the quantum world. Ponder how a particle's fuzzy probability cloud could possibly relate to the sharp geometry of Einstein's cosmos. This step-by-step approach builds your understanding logically, layer by layer. Above all, be patient with yourself. Your brain has spent a lifetime learning a Newtonian language of absolute space and time. Learning to think in space-time is like learning a new language as an adult. It feels awkward and unnatural at first. You will have moments of confusion and frustration. But with repeated exposure, with consistent practice in drawing, reading, and discussing, the new framework will slowly take root. Your intuition will begin to shift. You will find yourself instinctively visualizing the world lines of passing cars or the light cones of distant events. Carl Sagan once wrote that somewhere, something incredible is waiting to be known. That incredible thing is a new way of seeing. By actively practicing, you are not just learning physics, you are rewiring your own perception, learning to see the invisible threads of spacetime that weave together the cosmos. The rigid geometry of the light cone seems to carve our future into stone, a fixed destination within the block universe. If every event from your birth to your last breath is a permanent point in the four-dimensional loaf, where does that leave our cherished notion of free will? Are our choices genuine, or are we merely reading lines from a script written at the beginning of time? This is not just a philosophical puzzle. It strikes at the heart of ethics and moral responsibility. If the future is already written, can we truly be held accountable for our actions? Philosopher Tim Maudlin argues that the block universe picture does not necessarily negate free will. Our decisions and deliberations, he suggests, are themselves real physical processes woven into the fabric of space-time. Your choice to act kindly is not an illusion. It is a real event that causes other real events within your future light cone. The block universe contains the entire story, including all the complex causal chains of thought and decision that lead to every action. Your moral character is not erased by this view, it is eternally inscribed. This perspective shifts the focus from a mysterious, uncaused free will to the real, causal power of our brains and intentions within the physical world. The ethical implications become even more striking when we consider potential future technologies. While purely speculative, the theoretical manipulation of wormholes or cosmic strings could, in principle, create closed time-like curves. The mere possibility forces us to confront the foundations of ethics. If you could travel to the past, the Novikov self-consistency principle suggests the universe would prevent paradoxes. You could not kill your grandfather, but could you subtly influence him? The ethical nightmare would be a form of historical tampering, where responsibility extends not just forward in time but backward. The causal power of your actions would loop back on itself, creating a feedback of obligation that challenges our linear understanding of blame and consequence. Yet relativity itself provides a profound ethical anchor. Our sphere of influence is not infinite. It is precisely defined by our future light cone. We cannot be responsible for events in the elsewhere, for galaxies so distant that our decisions today will never reach them. This cosmic limit grounds our morality in the local and the achievable. We are tasked with caring for the world within our causal reach, for the people and the planet whose futures we can genuinely affect. Our responsibility is not diminished by this, it is focused. We are stewards of our own light cone, architects of a future that, from our perspective inside it, is still being built choice by choice, action by action, within the magnificent and unchangeable architecture of spacetime. Your journey into spacetime does not end here, it has only just begun. To truly build your intuition, a hands-on approach is invaluable. Start with the classic book Spacetime Physics by Edwin Taylor and John Archibald Wheeler. This is not a dry textbook. It is a workbook for your mind, filled with problems that train you to think in diagrams and world lines, making the geometry of relativity feel as natural as a map. For a breathtaking journey into the frontiers where relativity meets the quantum world, Brian Greene's The Elegant Universe provides a masterful narrative, unraveling the mysteries of string theory and hidden dimensions with stunning clarity. If you prefer a more philosophical and lyrical exploration, Carlo Rovelli's The Order of Time will challenge your deepest assumptions about the flow of time itself. To structure your learning, online platforms like Coursera and edX offer full courses on special and general relativity, often taught by leading university professors. These provide a guided path through the mathematics and concepts, complete with problem sets and community discussion. For daily doses of cosmic wonder, YouTube channels are a fantastic resource. PBS Spacetime delves into deep topics like black hole thermodynamics and quantum gravity with detailed animations. Veritasium excels at creating compelling, experiment-driven explanations that make abstract principles feel immediate and tangible. To see the universe through a relativistic lens, try interactive software. Spacetime diagram simulators allow you to plot events and world lines, watching how they transform between frames with a click of your mouse. Planetarium software like Space Engine can show you what the night sky would look like from a spaceship traveling at a significant fraction of light speed, where the stars distort and colors shift due to the aberration of light and Doppler effects. When questions inevitably arise, do not learn in isolation. Online communities like the Physics Stack Exchange are gathering places for students, enthusiasts, and professional physicists. You can post your own questions about the twin paradox or light cones and receive detailed, thoughtful answers from people who are passionate about sharing their knowledge. These resources are your toolkit for building a lasting understanding. They transform the passive act of watching a video into an active exploration, empowering you to move from curiosity to mastery, one diagram, one book, and one question at a time. This journey through spacetime leaves us with a profound new vision of reality. Space and time are not separate stages but a single, dynamic fabric, a four-dimensional continuum where every object carves its permanent world line. Our measurements of length and duration are not absolute truths, they are personal perspectives, shaped entirely by our frame of reference. This relativity is not chaos, it is a deeper harmony, governed by the absolute speed of light and the immutable geometry of the light cone. These cones are the universe's ultimate traffic laws, rigorously separating the possible from the impossible, ensuring that a cause always comes before its effect. To think in these terms is to acquire a master key, unlocking mysteries from the precise ticking of a GPS satellite clock to the violent, inescapable grip of a black hole's event horizon. It transforms our place in the cosmos from passive observers to active participants in a reality woven from multiple, equally valid viewpoints. This perspective demands both curiosity and humility, a recognition that the universe is far stranger and more wonderful than our everyday senses suggest. The great physicist Stephen Hawking offered a simple, powerful piece of advice. He said, "Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist." Carry this sense of wonder with you, question the nature of time, ponder the architecture of causality, and look at a passing train not as a simple thing, but as a window into the fundamental structure of existence. We would love to hear what surprised you most on this journey. Share your own thoughts and questions in the comments below. If you are eager for more deep dives into the wonders of the cosmos, be sure to subscribe. Never stop being curious.